Morning, dear students. In yesterday's lecture, we have studied regarding electrode potentials of different electrodes. In today, we will discuss on the topic EMF of a cell. Now, EMF stands for what? It stands for electromotive force. How we can define this? This EMF of a cell arises because of difference of electrode potentials of two electrodes. Whenever we connect one electrode to the other electrode, what we will see, there is flow of electron taking place from one electrode to the other electrode. And why this flow of electron is taking place? This is arising because of difference of electrode potentials of the two electrode. And this is known as EMF of the cell. This force, which is responsible for the flow of electrons from one electrode to the other, is known as EMF of the cell. And it is measured in the unit of volts. So how we can define this? This is the difference between the electrode potentials of the two electrodes which are constituting an electrochemical cell is known as electromotive force or cell potential of a cell. Now what we will observe, the flow of current is taking place from the electrode at higher reduction potential to an electrode at lower reduction potential. And the electrode at higher reduction potential is taken as cathode. So we can say the EMF of the cell will be equal to reduction potential of cathode minus reduction potential of anode. And when there will be the standard EMF of the cell, standard EMF of the cell will be equal to the difference in the electrode potential which are under the standard conditions taken. So we can say this is equal to standard cathode potential and standard anode potential. And in terms of reduction potential, we can say this is the difference between the reduction potential of cathode and anode under standard conditions. Now how we can measure the EMF of a cell? EMF of a cell can be measured by connecting the two electrodes to a voltmeter directly and taking the reading. But in this method there are two objections. Now what are these objections? Whenever we connect it directly to a voltmeter, you will see the voltmeter draws some current from the cell. So EMF of the cell will change. So how we can calculate the correct EMF of the cell if EMF of the cell is changing? Second thing, due to appreciable flow of current, a part of EMF is also used up to overcome the internal resistance of the cell. So this again will change the EMF of the given cell. So these objections are overcome by potentiometric method of measurement of EMF of a cell, which is based upon Pogendroff's compensation principle. Now how we measure the EMF of a cell by using this principle? In this case, we can see the circuit diagram of measurement of EMF of a cell using potentiometer. It consisting of a storage battery. This is the storage battery having voltage greater than that of the cell to be measured. The cell whose EMF we have to measure, that is connected to this storage battery in this circuit. Here we are having a stretched wire of uniform thickness which is AB. Next one, a standard cell whose EMF is already known is connected to the galvanometer G and put into the circuit first. Now what we do, we move the sliding contact until and unless the fall of potential between these 2 points is compensated by the EMF of the storage cell. So here at the point A and D, when the sliding contact is on D point, we are observing the EMF of the standard cell is compensating the fall of potential due to this battery. Now what we do, we repeat the same process by the unknown cell. Now we put this unknown cell into the circuit by connecting through galvanometer, and what we will observe on moving the sliding contact at point D dash, when there is AD dash, the fall of potential of the battery is compensated by the EMF of this unknown cell. So the EMF of unknown cell will be calculated by using the following equation. EMF of unknown cell divided by EMF of standard cell. that will be proportional to the distances used here. Here the distance will be AD dash by AD, as we are taken unknown cell up. So we will take here AD dash up and AD down. So you will have to correct it little. So EMF of unknown cell divided by EMF of standard cell will be equal to distance AD dash divided by distance AD. From this equation we will find out the EMF of unknown cell, as the EMF of standard cell is already known. So this is the Pogendorf's method of determining the EMF of a cell using potentiometric method. Now, what do we mean by a standard cell? A cell is considered a standard cell if it fulfills the following requirements. First one, it will have a constant value of EMF which is reproducible. By again and again measuring of the EMF of the cell, we are getting same EMF. So it means that cell is the standard cell whose EMF value is almost constant. Second thing, its EMF should not change with the passage of time. Third thing, it should have a very small temperature coefficient. Means that effect of temperature should be very small on the standard cell. Now next one concept is the concept of reversible and irreversible cells. So first of all, we must know what is the reversible process. Reversible process is carried out infinitesimally slowly, so slowly so that it can be reversed at any stage by increasing the opposing force slightly more than the force already acting. So a cell will be said to be reversible. Now we are talking about the cell. A cell will be said to be reversible if it satisfies the following three conditions. First one, if the opposite EMF is equal to the EMF of the cell, there should be no current flow and no chemical reaction. Second thing, if the opposite EMF is less than that of the EMF of the given cell, then should be infinitesimally small current flow and small reaction. And third thing, if opposite EMF that is greater than the EMF of the given cell, then there will be small current flow and small reaction in opposite direction, as in this case opposite EMF is greater than the EMF of given cell. If these three conditions are followed, the cell will be known as a reversible cell. Now the electrochemical cell which doesn't satisfy any one of the condition of reversibility, that will be known as an irreversible cell. Now taking the example of these two type of cell. First one is the reversible cell. We are taking the example of Daniel cell, in which we are having zinc immersed in the zinc sulfate solution, copper immersed in the copper sulfate solution, and they are connected through the salt bridge. So in this case, what you will observe, if we are applying an external EMF greater than the cell EMF, the direction of current as well as the cell reaction both are getting reversed. So such type of cell is the reversible cell. Now in case of an irreversible cell, we are having here the example zinc silver electrode. They have been dipped in the H2SO4, aqueous solution of H2SO4. So you can say dilute H2SO4. So how it is acting in this case, when the direct reaction is taking place, the zinc is acting as anode and silver is acting as cathode. The direction of current is reversed on applying the opposite EMF greater than the EMF of cell, but the direction of chemical reaction is not reversed when we are applying external EMF greater than the cell EMF. Now we can see this in the next slide how it is. First one, when there is cell reaction is taking place, normally there is no external EMF. In that case, zinc is losing 2 electrons to give zinc 2 plus, and hydrogen ion at cathode, which is the silver electrode, at Ag electrode, hydrogen ion are taking up these 2 electrons and converting to hydrogen. So in this case, hydrogen gas is produced at silver electrode and zinc is losing 2 electrons. So this is the net reaction taking place when there is no external EMF is applied. Now when we are applying the external EMF slightly greater than the cell EMF, what is happening here? You will see in this case at zinc electrode, the hydrogen ions are taking up the 2 electrons and producing hydrogen gas. And at silver electrode, the silver is losing the electron to give silver plus sign. Here we are taking 2 Ag, so there 2 electrons are released to balance the equation. So the net reaction in this case is this. So as we compare the net reaction, you will see the net reaction is not getting reversed. Although the direction of current is getting reversed, but the cell reaction is not getting reversed. So such type of cell will act as a irreversible cell. Now there are various type of reversible electrodes. Different type of reversible electrodes are metal-metal ion electrodes, amalgam electrodes, gas electrodes, metal insoluble salt anion electrodes, and oxidation reduction electrodes. We will discuss regarding these electrodes each one by one in our next lecture.